right, counting principles. So there's like one principal and three assistants. No, not those kind of principles. So how do we count? Right? You might think, I learned that at a very young age. 1, 2, 3, 4. But so what we have is the sample space, also known as the universal set. Okay, so we're right back into set theory. So set theory, counting, and probability. So last unit, this unit, and then the last unit, the final unit, are all, like, it might as well just be, in a sense, one big unit, right? So the same concepts are going to run through all three. So the sample space, also known as the universal set, is the set of all elements or outcomes under consideration for a particular context or experiment. These outcomes can be listed in an outcome table, in a tree diagram, or in set notation, right? So we've done set notation, right? That's what last unit was all about. Strategies for solving counting problems are a tree diagram, which we're about to do, so you'll see what that is. The fundamental counting principle, which we will also be doing, and Venn diagrams, which we have done. Okay, so in the Venn diagrams, right, you've got those different areas. You're putting the number in. We're asking you how many drank both tea and coffee or something like that, and you've got 4 numbers in a two-circle Venn diagram. You've got those 4 sections. You put the numbers in, you figure out, right? We did some adding, subtracting. Oh, we got 76 left to place, but there's only 57 spots, so that means 19 or whatever. Did both. And we did that using a Venn diagram. All right, so a tree diagram. Ms. McKay has 4 different necklaces to choose from: silver, gold, pearls, and diamonds. She has 2 different pairs of earrings, pearl studs, and gold boots. Create a tree diagram to show how many different variations of jewelry Ms. McKay can choose from each day. So we call it a tree. It's really kind of a tree laying on its side. And what we do is we start with the beginning, right? And then we have the first branch. And the first branch here is the necklace. And she has 4 different, so there's going to be 4 branches to this. Let me just redraw that. So 1, 2, 3, 4, right? She has 4 choices of necklace. And we'll label them. So silver, gold, pearl, diamonds. So that's the first thing that we're choosing is the necklace. Then we're going to choose the earrings. And so if she chooses a silver necklace, what kind of earrings can she match with those? How many choices does she have for her earrings? 2. So we'll call that PS and GL. So if she chooses the silver necklace, she can choose pearl studs or the gold loop. If she chooses the gold necklace, what choice does she have for earrings? Yeah, the same 2, right? If she chooses the pearl necklace, what choice does she have for earrings? Again, those same 2, right? She always has the 2 choices for the earrings. If she chooses the diamonds, then pearl studs or gold loop. So one thing about doing a tree diagram is it's going to list every actual outcome in the sample space, right? And then we're just going to count them up. So we're trying to learn counting here, okay? This is one way to count. So what we do is let's follow each branch. So we could say silver with pearl studs, silver with gold loops. Each of these is an outcome. Gold with pearl studs, gold with gold loops, pearls with pearl studs, pearls with gold loops, diamonds with pearl studs, diamonds with gold loops. So here's what we do in a tree diagram. So the first thing we're choosing is a necklace. Okay, and we have 4 choices for the necklace, right? After that, we're choosing earrings. And for each choice of necklace, we have 2 choices of earrings. And what we do is we'll follow each branch, right? So this branch is the silver necklace with the pearl stud, the silver necklace with the gold loops, the gold necklace with the pearl studs, and so on. So how many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so how many different variations? There are 8 variations. Now, when you do a tree diagram, you're actually going to list each of the variations, right? And sometimes we may actually want to see that, right? Sometimes we just care about how many outcomes are there, okay? Like especially if it's a really large number of outcomes. So if we were doing something and there were 500 outcomes, we probably don't want to list each of them, right? We're doing something here that has 8 outcomes, and we might want to imagine, okay, what's it going to look like? So we say, well, you've got the silver with the star. I can imagine what that looks like. I can imagine what each of those will look like, and then make my decision based on having a list of them all. Okay, so 8 variations. And that's your tree diagram. In the fundamental counting principle, for a task made up of several stages or parts, so this task will be made up of 2 parts, right? Choose the necklace, choose the earrings. The FCP, the fundamental counting principle, states that if the number of choices for the first stage is A, so for us, the number of choices for the first stage was 4. And the number of choices for the second stage is B. And the number of choices for the earrings is 2. And if there were a third choice, third stage or something, maybe she has a couple of different watches that she wears, or rings or whatever, that could be a third stage. That was C. Then the number of ways in which the task can be completed is to multiply each one together. So the fundamental counting principle will give us the number of ways something can be done without necessarily listing each individual way. Yeah. Oh, thanks. Like Breaking Bad Thursday. We got Catcher Tuesday, then Doctor Who on Wednesday.
It's a rotation.
Yeah, I don't have enough Breaking Bad shirts to go more than a few weeks though. All right, so example of fundamental counting principle. So you've all seen these little combination locks, right? And down here it's got 0 through 9. And we want to know, you have to rotate the wheel to get the correct code value. So how many 4-number codes are there if the first digit can't be a 0? Wait, let's do this too. How many 4-digit codes are there? So here's how we do a fundamental counting principle question. What you do is you put down the number of choices, right? Because we've got 4 digits. And you put a multiply in between them, right? Fundamental counting principle says, so your first stage here is the first digit in the combination. The second stage is the second digit in the combination, and so on. All right, how many choices do I have for the first digit? So 0 through 9 is 10 choices, right? How many choices do I have for the second digit? Well, again, it's 0 through 9, right? So 10 choices. How many choices for the third digit? Wait for it. 10. And for the fourth digit?
7.
Yeah. So this particular lock, or anything like it, has a total of 10,000 possible choices. Okay. I would say combinations. We actually, of course, we call it a combination lock. That's actually misnamed, but we'll get to that in a few days. And we'll still call them combination locks, even though they're not. But. So how many 4-digit codes are there? So I have 10 choices first, then 10, then 10, then 10, 10 times 10 times 10. 10 is 10,000. What if the first digit can't be a 0? Then how many choices are possible? You're going to have to squeeze. So again, anytime you do a fundamental counting principle, put down a line, a blank line, for your first choice, then multiply, right? Then the second choice, then third, then fourth. In this case, 4 choices. So if the first digit can't be a 0, how many choices do I have for the first digit? So there's 10 normally, but it can't be 0, so we have 9 choices. All right, then what? How many choices do we have for the second digit? 10. Okay, so there's a lot of interpretation that goes into these three units, right? When you're reading, you gotta, okay, did they say anything about the second digit? No. All right, so that's just normal. For the third digit, how many choices? And then for the fourth digit, and that will be a total of 9,000. Okay, so if you can't lead with a 0, then you have 9,000 choices. What if each digit can only be used once? So the way you're going to see that written is repetition is not allowed. Repetition is not allowed. So fundamental counting principle, again, anytime we work it out, we're putting down 4 blanks because we are choosing from 4 digits. Okay, I can't repeat. How many choices do I have for the first digit? 10, right? Everything's open. How many choices for the second digit?
9.
For the third digit?
8.
For the fourth digit?
7.
Somebody work that out.
5,040.
That's actually going there. 5,040. Yep, you're right. 5040. So if you can't repeat digits, 5,040. Okay, so we said we got a few ways of counting, right? So example. So tree diagram, which actually lists, this is the sample space or the universal set, right? This is the set of all possible outcomes. There are 8 of them, but each one of them is listed. Here, there are 10,000. We are not going to list them all, right? You could 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 9, 9, 9, 9. We're not going to list them, okay? We want to know how many there are, but we don't want to list them all, right? That would be ridiculous. 10,000. All right, using a Venn diagram, we can count. So, given a standard deck of 52 cards, state the number of possibilities of drawing a single card and either getting a red face card or a 5. Okay, so when we're doing Venn diagrams, we have to ask, is there any overlap? So, are there any cards which are both red face cards and 5s? No. Right? There's no card. You can't pull a card out of the deck and say, oh, it's the Jack of 5. No, right? You got Jack of Hearts, Jack. You red face cards. You have 5. Those are mutually exclusive, right? They both can't happen. So the sets are disjoint. No common outcomes. So if these are the red face cards, how many red face cards are there?
8. No, 6.
6. How many 5s are there? I might list it like this. Okay, there are 4 5s. Okay. So, what's the chance? How many ways are there getting either a red face card or a 5? How many ways can you do that?
10.
10 different ways, right? So 6 plus 4 is 10. So remember, or is a union, put them together. So there's 6 of these, 4 of those. Out of the 52 cards, there are 10 of which are either a red face card or a 5. Either a red card or a jack. Are there any red jacks? Yes. Which ones? Jack of diamonds, Jack of hearts. So if we call this set red and this set jack, now we got a couple things we could do. We could put an image of each red card in there, right? But we want to count. We're using Venn diagrams for counting. So how many red cards are also jacks? How many red jacks are there? You already said this, right? 2. So in here there's 2. How many jacks are there in total? 4. So how many go out here? 2. So there are 2 which are red and jack. That's what this section is here, right? Both red and jack. How many red cards are there in total? So how many are out here? So there are 26 red cards, right? Half the deck is red. So what we would say, there are 24 cards that are only red, right? They're only red but not a jack. There are 2 cards which are only jacks but not red, and there are 2 cards which are both red and jack. So, how many ways are there getting either a red card or a jack?
2.
28. I know you're saying 2. So there's 24 red, but not jack, right? There's 2 which are red jacks, and there's 2 which are. So the number of ways that you could draw a card out of the deck and get either a red card or a jack is 28. See, what we don't want to do is this. So without using a Venn diagram, we would say, hey, you got 26 red cards, you got 4 jacks, right? 26 plus 4 is 30. Okay. Then we got to say, wait a minute. You counted 2 of those cards twice. You counted the jack of hearts and jack of diamonds as a red card, but then you also counted them as a jack. So we're going to learn how to work our way around that. Red card or a heart. So is one of these a subset of the other?
Yes.
Which one? Okay, so hearts are a subset of red. So how many hearts are there?
13.
13. How many red cards are there? So how many cards go outside of the heart circle but inside the red circle? 13. What are they called?
Diamonds.
Yeah, they're called diamonds. Now actually, while I'm at it, we should put in the other cards, right? So in the universal set, if we have the 6 face cards and we've got the 6 red face cards, and we've got the 5s, then outside of that we have 42 other cards, right? Like inside the box, there should always be a total of 52. So I just kind of filled that in, make sure we know that, well, that's 10 of the cards, here's the other 42. They aren't red face cards, and they aren't 5s. Yep.
I think for the second one, that's 52.
Yeah, I just saw that. But yeah, I mean, 28. Right, I did that not on purpose. And so here, there are 26 red cards, right? But the hearts are a subset of those red cards. There are 13 of them. There are 13 red cards that are not hearts. They're called diamonds, but we're not asked. And then there are the 26 black cards, which are in the universal set. So this is a way that we can count using a Venn diagram, right? And then we did a lot of that in the set theory unit. We did a lot of counting using Venn diagrams. For mutually exclusive events, the sets which are disjoint, the number in A union B is the number in A, here, 6, plus the number in B, 4, right? Because there's no common outcomes. We're not counting anything twice. But if the tasks are not mutually exclusive, if the sets are disjoint, then we take the number in the number in the union. So let's take this one here. If we did reds, so let's do this. We'll do the number in, let's do it over here. The number in red union jack. Union jack, it's an old flag. The number in red union jack would be the number of red. How many red cards are there? There's 26, right? Plus the number of jacks. How many jacks are there? So 26 plus 4. But then what have we done? We've counted the jack of hearts and the jack of diamonds once as a red card, and then we counted them again as being part of the 4 jacks. So we have to subtract minus the number of cards which are both red and, right, intersection means and. So union is or, intersection is and. So how many cards are there that are both red and jacks? Minus 2, right? Which would be 30 minus 2, which is 28. So if the sets are disjoint, it's mutually exclusive, there is no and, right? There is no common outcome. So you can actually use this formula for that. So let's just do this one. We do red 5s, right? So red union 5 is the number of reds plus the number of 5s minus the number of red and 5. So 20, oh sorry, red face cards. Okay, go back here. Number that are red face union 5. So the number of red face cards, which is 6, plus the number of 5s, which is 4, minus the number of cards which are both a red face card and a 5, which would be 0. So, given these two formulas, if you accidentally use this formula or use it when you don't have to, this is just going to be 0. It's not really going to matter. Right? So if you're not sure which formula to use the one with the and. Okay? Because if it's the wrong formula, it's not going to matter. And again, you're going to see those formulas. Now they're listed with a capital P, which stands for probability. Right? So we're going to use these formulas. The ones we're using here with the n, but anything with a capital P, you can use with a lowercase n. So anywhere you see on this formula sheet that capital P, you can just think, I can use that exact same formula, but with a lowercase n for the number of, right? Because we just want to count. So sometimes we don't want to do a Venn diagram, okay? And then we don't have to, we can use this formula, right? And it is on the formula sheet. All right, practice. A football team has the following tips. One of those football teams that doesn't actually pick up the football. A red or black jersey, white, red, or black pants, and red or white socks. The team plays in a different uniform each week until it has to repeat a previous uniform. Determine how many weeks the team can play before repeating a previous uniform. Okay, so we could draw a tree diagram, right? And if we wanted to imagine, in our head, what does this look like? Then a tree diagram would list each of the outcomes, right? And we could say, all right, so we could be in all red, right? We could have this red, we could go red and then white, and then white, we could go red and then white and then red. Okay, but we're just interested in how many. So instead of drawing a tree diagram, we're going to use fundamental counting principle. So that says, put down 3 blanks, right? So we got jerseys, we got pants, we got socks. So how many choices do we have for the jersey? 2. How many choices do we have for the pants? How many choices do we have for the socks? What's 2 times 3 times 2? 12. So if they play 1 game a week, they can play for 12 weeks before they're going to have to repeat a uniform. Okay? Now, if we wanted to, again, we could do the tree diagram. I'll show you kind of what it would look like. We go here, we say jersey, right, red or black, and then we got pants. So there's 3 pants coming off of there, which is white, red, black, and then off of here we've got socks, which is 2. So you can see in this branch, right, for the red jersey we have got 3 of these and 2 of these. So if we just look at the white pants, we'd say there's 2 choices. Every time you wear white pants, you've got 2 choices for the socks, right? But you got 3 choices of pants, so 3 times 2. And then you got 2 jerseys, right? So 2 times 3 times 2. So if you did need to list the sample space, a really good way to do a sample space is to do a tree diagram, because you won't miss anything and you won't list something twice. If each of the students in a homeroom class of 30 students is capable of winning any of the class prizes, how many ways are there of awarding a math prize, a chem prize, and a physics prize? All right, so how many students could win the math prize? 30, right? 30 kids in the class. How many students could win the chem prize? How many? 30, right? Can you win both? Well, it doesn't say you can't. So for each prize, there are 30 students. So how many ways could those 3 prizes be distributed? 30 times 30 times 30 is 27,000. Okay, fundamental counting principle. We got 3 prizes, math, chem, physics. 30, 30, 30. What if we have a first prize, a second prize, and a third prize, which means you can't really win more than 1 prize, right? So for something, you're either in first place, or second place, or third place. So how many kids could come in first?
30.
30. How many kids are there left that could come in second? Okay, so you can't win first and second prize, right? If you win first prize, you're not eligible for second. How many students are left that can win third prize? And what is 30 times 29 times 28? 24,460?
Mr. Yanover, there's a really, really high-pitched ringing that is, I don't know if anyone else can really hear it at all. Okay, I don't know where it's coming from, but it's really high-pitched.
A vehicle license plate used to, now it's like different, but it used to consist of 3 letters followed by 3 digits. Okay, so 3 letters, 3 digits. How many different plates would be possible if there are no restrictions? All right, so here's how fundamental counting principle works. 3 letters, 3 digits. So letter, 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 digit, digit, digit. Okay, you don't have to label underneath them if you don't want. So if there are no restrictions, how many letters are possible for the first letter? That's where we find out if you know how many letters are. Some people don't. It's weird. 26. How many letters are possible for the second letter? Okay, so no restrictions means, so what you're often asking yourself is, when we do these types of problems, one of the big questions to ask yourself, are there any restrictions? Is there anything I can't use? And this says no restrictions. So the third letter, how many choices? For the first digit, how many choices?
10.
Second digit.
10.
Third digit.
10.
All right, so 26 times 26 times 26 times 10 times 10 times 10. 17 million.
576.
Like so? So why? Right? Like, why did they have to change the, what is it now? It's like four letters and 3 digits? Okay, well, the reason why they did change is, well, okay, first of all, what if we can't repeat letters? So again, so a big part of these last 3 units is the interpretation. Okay, if I can't repeat letters, I'm just going to throw letter, 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 digit, digit, digit. So how many choices do I have for this first letter? 26. For the second letter? 25. For the third letter? For the first digit? Second digit? Good. Third digit? Okay, what's that work out to? How much? 15 million. See, I thought you said 50 million. It can't be bigger. Remember, I can't hear. Glad you heard me just fine. 15,600,000. The letters I and O cannot be used. So this is why, right? There are certain letters they don't let you use. You don't want to use an I and an O because it could be confused with this 1 or a 0. So the letters I and O cannot be used. Okay, so give this one a try on your own. So again.
But can you still use
Try it. Interpret it yourself. Just make sure you're using a pencil. So put your interpretation on this, right? Like pretend, okay, this is the test now, and they're asking me this question. How am I going to interpret this? All right, and it's okay to interpret it wrong. Now's the time to do that, right? It doesn't cost you anything. You just, oh, I thought that. All right, I got it now, right? So, how many people think it's that? All right, see if you. What does that work out to?
13,821,000.
Okay, does that fit? Okay, if you didn't think it was that, if you look at that, you say, yeah, okay, I see what you did there. Now, sometimes what they'll do is, it'll be a question like that, and they'll give you an example, and in the example, maybe you'll see the letter B twice, and if you were asking yourself, can I repeat letters? Then the example says, okay, obviously you can repeat letters. Okay. Now, if you can't repeat things, you're often going to see the words without repetition, right? And the way I like to think of that is like it's on Scrabble tiles or something. They're in front of you. Once you choose it and use it, you can't use it again. With this one, it's like, yeah, it doesn't matter, right? You can put any letter on. They're not on Scrabble tiles. An area in Calgary has phone numbers that start with 403 and have a prefix of 253. How many different phone numbers are possible? So how many digits are we choosing? 4, the last 4, right? Can we repeat digits in a phone number?
Yes.
Okay, so then your choices are? It would be 10,000 again. So just like the combination law, right? And we all know phone numbers, and so therefore we all know you can repeat digits in a phone number, right? It's not something where repetition. But here, repetition. All right, given the digits 2, 3, 5, 7, and 9, how many 4-digit numbers are formed if repetitions are allowed? All right, so 4-digit number, fundamental counting principle says put down 4 blanks, right? You got to start there. There are 4 things. We are not going to draw a tree diagram because there are way too many of these to really want to list. If we really want to list them, we could sit down, write a computer program, and list them all. But all right, so how many choices do I have for the first number, first digit? 1, 2, 3, 4, 5 digits. Okay. So 5. How many choices for the second digit? 5 again. And then? And then? And that is? Yeah. No, you're right. I went too high. I was going to the next one. I outsmarted myself. Not very smart. Use these digits only once each. Now, another way to say that is repetition is not allowed. Okay, so you'll often see repetition is allowed, repetition is not allowed. Again, okay, we're doing a fundamental counting principle problem. We're going to put down 4 blanks because we are doing 4 digits. First digit, we have how many choices? And then, and then, and then, which is, let's get in there. Now, every time we do a fundamental counting principle, I'm always going to say this and that, and, because the word and is associated with the operation multiply. Whereas the word or is associated with what? What did we do up at the top when we said there's 6 or 4? What did we do with the 6 or 4? So we said red face cards, there were 6, and they said 5, there were 4. So we said, what can you get? Either this or that. How many choices were there? 10. What do we do with the numbers? Add. So the word or, from this point forward, will now be associated with the operation add, which you should already know, right? Because when I wanted to do, bicycle or whatever, I was just adding up all the numbers, right? Union is adding up. Okay. Now it turns out that and goes with multiply. Using these digits only once each, and the number must be even. Okay, here's how we're going to deal with this. We're going to put down the 4 blanks. The number's got to be even. What does that mean? So the last number has to be even. How many choices do we have for the last number? 1 choice. So what we do, when there's restrictions, we deal with the restrictions. So this must be the 2, right? The 2. How many 2s do we have to choose from? So for the last digit, we have 1 choice. It's got to be a 2. Now, if the number, if there was a 4 in there or a 6, then we would have like 3 choices for the last number, right? Any even digit would make the number even. Okay, we can only use digits once each. So look at this. We have 5 digits, right? But we put the 2 in last place. So how many digits do we put in the first place? And then? Okay, so the restrictions are off now. So we got 4 choices, and then 3, and then 2, which is 24. Should be more. Is that it?